In this experiment, we want to compare the theoretical and practically determined values for the equivalent resistance of two resistors in parallel. We're going to use this circuit, and these are the two resistors in parallel that we are referring to. So we're going to determine the equivalent resistance of those two resistors in parallel in two different ways. Theoretical and practical. And then we're going to compare what we get from those two different ways. First, we need to understand some theory. How does adding resistors in parallel affect total resistance? So you should predict which of these three LEDs is going to shine the brightest. Which of these three ammeters is going to give the highest reading? Which of these three circuits has the highest and which has the lowest total resistance? We can see that the difference between these three circuits is the number of resistors in parallel. In all cases, we have 1K resistors, but here we only have one 1K resistor. Here we have two 1K resistors and they are in parallel with one another. And here there are three 1K resistors in parallel with one another. So how does adding resistors in parallel affect total resistance, current strength in the main part of the circuit, and the LED brightness in these circuits? Pause until you've answered that yourself. To help us to think about this, let's liken these parallel sections to sections of water circuits. So it's only the parallel section, well, obviously in the first case it's not even a parallel section, but it's only the parallel section that is shown in these water circuits, not the entire circuit. And in each case, we have good conductors represented by thick pipes. And in each case, the water needs to move from the thick pipe on the right through the thin pipe to the thicker pipe on the left. Just as in the electric circuits, electric charge needs to move from the good conductor on the right through the resistors and then to the good conductor on the left. Now for the water to do that, it has to travel through the thin pipes. Just as for the electric charge to do that, it has to travel through the resistors. In the first circuit, we only have one resistor. Just like over here, we only have one thin pipe. All the water needs to pass from right to left through that one thin pipe. In the second circuit, we have two resistors in parallel with one another. Just like in the water circuit, we have two thin pipes in parallel with one another. So as the water moves from right to left, it has a choice. Some of the water moves through the top thin pipe to get to the left and some through the bottom. In the same way, as the electric charge moves from right to left, some of it travels through the top 1K resistor and some of it through the bottom 1K resistor, and then all of it then travels through the main part of the circuit shown there on the left. In the third circuit, there are three paths for the water to travel through, just as there are three paths for the charge to split between. Some travels through each of the three paths, and then the charges reunite into the main part of the circuit again. So if we look at these top water analogies, in which case will it be easier for the water to flow from right to left? In the third case, because there are more paths for the water to flow through from right to left. These three thin pipes add up to make a thicker overall, or we could say effective pipe. In a similar way, in this circuit, it's easier for current to flow because the three resistors act like pipes in parallel so that together they make like a thicker pipe. So their effective or equivalent resistance is easier, lower. So we get a greater current strength flowing in the third circuit's case because it's easiest. And we get the lowest current flowing when we only have one resistor, when we have no branches, no parallel sections, the first circuit. So what does this tell us about the overall resistance of the three circuits? How does adding resistors in parallel affect the total resistance? Where it's easier, there must be lower resistance. Here it's easy for current to flow, meaning the total resistance is low. Where it's more resistant, that means it's more difficult. Resistance refers to how difficult it is. So here it's difficult for current to flow. There's a high resistance. We can see that resistance and current strength are inversely proportional to one another. When one is big, the other one is small. Also in the third circuit, the LED shines the brightest. In the first circuit, the LED shines the dimmest. which matches the other information that we discussed earlier, that the total circuit resistance is greatest in the first circuit, so there's a low current strength through it, so the LED doesn't shine very brightly. But in the third circuit, because the total resistance is so low, the current strength flows at a high rate throughout the circuit, including through the LED, and so the LED shines brightest. So let's get back to the circuit that we're going to use in this particular practical. We're going to have a battery, and it will be connected to a 1K resistor which is in the main part of the circuit, and that will be connected to two 1K resistors in parallel with one another. And it's that parallel section that we're really interested in. Now in this circuit diagram here, we've replaced that parallel section with a single resistor having equivalent resistance, having the same resistance as the two resistors in parallel. So you can see there's the 1K resistor, there's the battery, and then in both cases we have ammeters. So we've already discussed that adding resistors in parallel decreases total resistance. So we know that this R equivalent must have a resistance less than 1K, because the equivalent resistance is less than any of the individual components in the parallel section. Adding resistors decreases resistance. But how do we know exactly what the value will be? Yes, we see it must be less than 1K, but how much less? Now in this particular case, it's actually quite easy to see what the equivalent resistance is. Why? Because the two resistors have the same value as one another, 1K and 1K. And whenever two resistors in parallel have the same value as one another, their equivalent resistance is half of that value. So half of 1K is half a K. In other words, 0.5K. Why does that make sense? Because remember, these two resistors in parallel together are as if they are a thicker pipe. And in this case, because they are both the same value, it's a double thicker pipe. The two resistors' thickness added up makes double thickness pipe. Double thick pipe is like half resistant. But let's also use these two methods. In any case, when you have resistors that don't have the same value as one another, you cannot just say it will be half the value. So we need to know how to use these two methods. The first method can be used if you have 2 resistors, 3 resistors, 4 resistors, 20 resistors, however many resistors you like. Method 1 will work. And in method 1, we say 1 over Rp, where Rp is the equivalent resistance. Sometimes we call it the effective resistance or the total resistance of the parallel. That's what the P stands for. Of the parallel branch, the parallel section. So 1 over Rp is equal to 1 over R1, so this value inverted, plus 1 over R2, the value of this resistor inverted. If we had a third resistor and we called it R3, then we just add in plus 1 over R3 and so on. But in this case, we do only have 2 resistors. So that's method 1. Method 1 works with however many resistors you like. Method 2 only works for 2 resistors in parallel. Again, we have Rp, equivalent or effective resistance of the parallel section. This method is quite nice because now it's not 1 over Rp. It's just plain Rp. Rp equals the product of the 2 resistors, the value of this resistance multiplied by the value of that resistance, divided by the sum of the 2 resistors. This resistance plus this resistance. And they will give the same value as one another. Method 2 is easier to use. So if you only have 2 resistors, it's a good idea to use it. But you must know how to use method 1 too, because it's the only one that works when we have more than 2 resistors. So that's how to determine the effective resistance theoretically. How do we determine it practically? Remember that resistance is equal to potential difference across the resistor divided by the current strength through the resistor. So here we have the parallel section, and we want to know the effective resistance of the parallel section. So to get that, practically, we must measure the potential difference across the parallel section and divide that by the current strength through the parallel section. Now let's just quickly speak about the current strength through the parallel section issue. You remember, of course, that in a parallel circuit, the current in the main part of the circuit splits, and some of it goes there and some of it goes there, and then it reunites. So it might seem a little confusing to speak about the current strength through the parallel section, because which current strength now? Is it before it splits or after or what? But it shouldn't be confusing, because can you see that the total current strength through the parallel section is equal to the current strength in the main part of the circuit? In other words, that which is measured by the ammeter. Because all the current flows through the parallel section, not all of it goes through each branch. But if you add the two branches' current together, then you'll get the main current. So it's the main current that goes through the whole parallel section. So that's why we can use the ammeter reading in this equation.